Alright, so first off, I'm not in my usual recording location, but I'm just in, I got a whiteboard now. So, today's problem is differentiating an equation to be able to plug into coding to find the ever-changing height based on the change in initial flow rate. So to do that, we need to start by looking at a very simple differential equation. And we're going to start with looking at, I know you probably can't see it with the glare here, but there's this, we get the volume of the tank. So let's go ahead and say V is equal to the integral of cross-sectional area with respect to height from 0 to whatever height we choose. And we can say that's true because if you have a chart, or if you graph that, as height goes up, cross-sectional area also goes up, and the space under that curve, I think it's see right in that, the space under that curve there is volume, and that's the area under the curve. And volume is equal to the flow rate in minus the flow rate out. And we get V is equal to Q in minus Q out. And another thing, the only thing separating volume from height is cross-sectional area. So dV dt is equal to the cross-sectional area times dH dt. And I know that's probably not the most convenient place to write it, but I have limited room. So with establishing that relationship, we can then determine that from Bernoulli's equation, V out is equal to V over 2, V squared over 2, and that is equal to G8. That's not it, that's not G. And that is equal to GH, gravity times height, and because that's how much pressure is at the bottom of the tank. And solve that out to mean V out is equal to the square root of 2GH. But then there's more, because we also have to take into consideration the size of this hole here, which I have all these values written out for the problem later when we code. I have the height is 8 meters of this tank, the radius at the top is 5 meters, the radius at the bottom is 1 meter, the flow rate is, we'll get there in a minute, but the cross-sectional area at the bottom is 0.01 meters cubed. That, I'm not going to put that in, but we actually have to take away this radical and go that height times the radical of 2GH. And then we can plug this into this top equation here. We've got V is equal to Q in minus AH squared into GH. I'm sorry, I said volume is equal to Q in, Q out. It's actually the change in volume with respect to time. Should have put that first. So I'm wrong. And to turn this equation into dH dt, all we have to do is multiply it by the cross-sectional area. So then we pull out cross-sectional area, AC, dH over dt is equal to Q in minus AH squared root of 2GH. And if you want to simplify that, it's dH dt is equal to this gobbledygook over the cross-sectional area. I don't know if you can really, I think you can see that okay. All right. So we'd almost be ready to put this equation here into code, but this is an initial value problem. So then we need to have a height term and an initial Q in term, like I was saying earlier. So Q in is pretty easy. We're going to set Q in equal to, let's say, zero point 0.1 meters cubed. That's 0.1 meters cubed per second. Yeah, because we need time there for it to be a rate. So we got that, and then Qn is also going to be equal to AC, and this is also going to be equal to AH, rather, square root of 2G, but not the regular height term that we were talking about. It's actually going to be...
Hi, you're probably wondering why I'm just suddenly popping in here like this. Well, I lost some video, so I gotta really quickly cover back what I lost. I think it was just like a little bit. So, I was right here. So, Qn is equal to 0.1 meters per second, and it's AH by 2G. And all I was gonna say is there's this H naught term here. Yeah, and it's to the half because it would be under the radical, but I took it out just because it's easier. And what I didn't get to explain was this H naught term here is equal to Qn over this, because you just do algebra to get H naught. And you come up with Qn 0 and AH squared, they're both squared, over 2G. And you can take this 1 over 2G term out. Alright, and now back to our regularly scheduled programming.
But just before we can actually start coding, we do need to do one more thing, and that is determine how we're going to go about getting the radius. And I'm going to sit down for this one since it's on the bottom of the board and I'm not kneeling. Alright, so can you see me? This a little closer. We need to use algebra and determine the radius, because that's the only way we're going to get the cross-sectional area with the height is radius. So I think you can see that. All right. We've got the r at the top, which we have set to 5 meters here, but for the sake of variables, I'm going to leave them as variables, no numerical values. And we've got the radius at the bottom, which is 1 meter. So we've got r bottom and r top, and that's on the y-axis. On the x-axis, we have the height, total height. And it's going to look like height is 0, radius is going to be the bottom, and it's going to be a straight line to right at the top, and that'll be the total height, which I believe is 8 meters in this example. So with that information, we can determine the radius at any given point is going to be the radius at the top minus the radius at the bottom over the overall height times the current height, and the intercept is going to be the bottom of the 2, because it's not perfectly, or bottom of the tank, because it's not perfectly 0. And now we'll actually be able to put this into code, which is what I'm going to do in the next step.
Alright, I hope this, as you can see, I've got a new environmental camera here. Hello! It's set up so for my class. Let me try to, there we go. Alright. So, this is the coding part for the conical tank that I just derived in that classroom. I'm back home now. I got kicked out of the class because I had class, so we're here now. And the first things we're going to do is, well, I already have this imported. This is just a whole bunch of, I'm pointing at the screen like you can see it. There's just a whole bunch of imports here to do to make our lives easier later, like plotly, we're just having a subplot, solve IVP, that's to solve the equation that we're going to be doing, and numpy, that's just for generic math purposes. So let's kick this off. We have all of our variables, and I have them written down here so I wouldn't forget. We've got, let's go ahead and start with, obviously G is equal to gravity, the gravitational constant. That is 9.81. We've got the whole is equal to 0.01. We've got, let's see, Qn, or at least the initial Qn, is equal to 0.1. The total height of the 8 meters, the radius at the top is equal to 5, radius at the bottom is equal to 1, and the simulation is going to run for 5,000, I think that's seconds. And we've got the initial height from that equation that we derived previously, and I believe that is Qn divided by AH, and it's all squared. And then it's again divided by 2G. Alright, I think we are set to run these, a new line of code, and then we can define that radius, which will just define the overall, defining the radius will define, what now? What's this? I'll fix that later. Call this tank. Let's set some parameters. I might get this in the wrong order, but we'll see. Okay, so I actually need to call this H total, and this is going to be H because we got to have the parameters as H total and not the height. So then we can go colons, hate colons. So then we define the radius as equal to the, let's see, I got the equation right here, R top minus R bottom. I'm probably going to need more parentheses. We've got over H total, and then times H, and then no, that last parenthesis, and then add the bottom because we're not completely at 0. So got that set. You want to return this multiplied by, I think it's np dot pi times np pi times r squared. I do believe that's the first equation that we've got to set. Run that. Oh, that ran all right. Why did you run poorly? There we go. Forgot about that. All right. Add some more code in here. So then the next equation that we need is to define this fluid level. Let's just call this FL. And the variables we need are T and H. No, I don't want that. Colon. So we gotta define Q in is equal to, I think the problem states we need a 1.2 or 20% increase. So we do this 1.2 times Q in 0. And then we need to define the cross-sectional area, which is equal to, I'm just gonna copy and paste this. That's right what that is. Pretty much. And then we return, I've got the equation written down here. I believe it's got to be an array. So, let's see if I can get this nomenclature right on the first try. All right. Qn minus, the differential equation was Qn minus AC. No, it was that small hole times, why do zeros keep popping up here? AH times 2 times GH. And then this 2GH is under a radical, so 5. All divided by AC. And I messed that up because I didn't even bother putting this second parentheses. So now we've got to solve this right-hand side with IVP. So I think it's numpy dot solve IVP. I can scroll up to make sure. Yep, solve IVP, and then we need the fluid levels. With respect to the time, there should probably be a comma in here, and then 0 to time, and then the array of H0 and then set dense output to be true. No, you're supposed to turn blue. Why aren't you blue? You're supposed to be capitalized? There you go. Okay. Dense output's true. And then we just need to, that's not right. Trash that. And then we just need to make some plots, so Boolean space, so we want linearly spaced 0 to 100. With and space it out with 5,000 little things in here because that's 5,000. H is going to be equal to the fluid level Nope, fluid level dot solution, because we want the solution from that solve IVP. And we want it to be it from T, and then we only want the first term. Okay, it's figure is equal to make subplots and then fig add scatter. And we want x to be this plot and y just simply equal to the height. Now let's see the fruits of my labor. This, of course it's broken. Why would it work on the first try? You mean numpy has no attribute to solve IVP? Backwards. It's supposed to be bracket, then parentheses. No? Is that not right? Also, I did some reviewing. Apparently, I'm supposed to set this equal to some sort of result is equal to solve. Yep, okay. And then I go, not the fluid levels. And let's go with, this has to be the result. Don't mind my spelling. All right. All right, back to Stack Overflow. Hey, Stack Overflow doesn't work. That's good to know. Unless I messed this up. No, this would actually have to be plot, wouldn't it? To make any of that work. Oh, we're getting somewhere. I don't know if I'm completely correct. That does not look correct. Let's see what happens if I raise it to the power of 10. Does it stabilize? It still doesn't stabilize. The height just keeps going forever. That's 100% wrong. Alright, so upon more careful consideration, I think I figured out kind of what I did wrong, and lies within these right here. Now let's look at it in an equation again, and it's supposed to be multiplied by this height, and then divided by the total height. This is added in post, but I'm going to bring around the rosy here. I just realized by order of operations, this fix that I made here is virtually meaningless. Like, probably wouldn't have changed too much. I'm going to leave it how it is, because I don't trust anything, but I think that could have been fine. I don't know if that's going to solve my problem of linearity. No, it didn't solve my problem of linearity, but it's a mistake that I caught upon more careful consideration. I still have to find the whole purpose, the whole reason why this thing is so linear. So code, and I want you to be h equals Yeah, it's definitely a problem with the height. Because that's not supposed to go above 8 byte for sure. And this is probably the problem right here. Is this solve IVP, because that's the only other... No, that ain't right. That probably is correct. But this is the only place where I have H. And I got H here too. Turn the array. Make sure this is okay. It's QA minus AH times 2. I already know I set these all right. 5, 1,000. Yep. Yup. Okay. I'm going to try one thing. I think I found a misplaced parentheses. It really was just that misplaced. Wow. Well, the simulation only said for 5 seconds, but it doesn't look like it's at steady state quite right, or quite yet. So you can run it even longer. 10,000. Oh, well. There's got to be a quicker way to do this than just manually going through each and every one of these. Okay, we're closer to steady state now. Let's just go to 70K. See what's done there. And now we're at steady state. Oh, looks like right around 50K is when you reach steady state-ish. You could really even argue that it's 40K, but it's still going on. Oh, it's ever changing. But it doesn't go above that 8. So we have, that's a 1.2% increase of our flow rate. And we can mess with this and go 1.1. That's not a 1.2%. And it reaches steady state far, far quicker. Well, 10,000 seconds quicker if you think that's far, far quicker. All right. I think that's a successful endeavor. Let's see H here. Yep, just keeps on going. All right. And our next video is going to be 3 tanks in a series.